This video will briefly go over the main physics concepts in analyzing vertical circular motion. So that's situations like vertical loops on a roller coaster, or planes undergoing vertical loops, or balls being swung around in a vertical circle. Okay, so here we'll have a look at an object completing a vertical loop, and this loop, as you can see, is circular. And as the ball rolls around the loop, it is undergoing circular motion. So we know that whenever anything is going in a circle, there must be a net force acting towards the center of the circle. And the interesting thing about this situation is that that force is upwards when it's at the bottom of the loop, and that net force must be downwards when it's at the top of the loop, because the center of the circle, when it's at the top, is below where the object is. Okay, so firstly, at the bottom of the loop, we have two forces acting, and they are the weight force and the support force. And, as we shall see, the support force must be bigger than the weight force to provide a net upwards force. So here, let's have a look at this. I'll try to pause it at just the right moment. Go back just a little bit. Oops, let's just rub that out. Pause there. Okay, so at this point we have a downwards weight force, which I'll call Fg, and we have an upwards support force, which I will call Fs. Actually, it'll be even bigger than that. Let's just rub that out. Fs. And if we add those two, we get the following. So the downwards weight force will look like this: Fg. I'm scaling it up a bit for this diagram, and F support looks like that, and that will result in a centripetal force that looks like this, or a net force that looks like that, from the tail of the first vector to the head of the second vector. So this is F net. So we can see here that the support force has to be considerably bigger than the weight force in order to produce a net force that's acting towards the center of the circle. Okay, so, or we can write that here as well. So F net here, oops, just pause that. F net here is going to be equal to F support minus F weight. So the length of this orange arrow is the length of the green arrow minus the length of the red arrow. In fact, I called it Fg, not Fw. Okay, so that's at the bottom. At the top, we have a slightly different situation. We still have two forces acting. We have a weight force acting, which is downwards, and we have a support force acting. But at the top of the loop, the support force is also pushing downwards. And because the weight force is acting towards the center of the circle, we only need a little bit of extra support force to make it keep moving in a circle. So we'll have a look and see what that looks like as well. So I'll just move that forward just a little bit to there. Whoops. There. So we can see here that the weight force is still acting downwards. Let me get a red one. And now we have a support force that's also acting downwards, like this. But it doesn't need to be very big because the weight force is already producing most of the centripetal force needed. And so in this case, we can draw the vector diagram like this. We have the support force. Oh, sorry, the support force is meant to be green. Let's keep the color coding the same. So the support force looks like this. And when we add these two, we get support downwards, and we get the weight force downwards, and we then get the net force is the sum of those two. And because both of the forces are acting downwards, they add together to produce the net force. And so we can write our equation for the net force like this. It's going to be equal to Fs plus Fg. I'm going to keep doing that. That's meant to be a G. Okay, so in this case, the two add together, which means that we don't need very much support force to produce this required net force. This is the net force here. So Fg contributes also to the centripetal force. So to summarize this analysis of the forces, so if an object is completing a vertical loop, there must always be a net force towards the center, and that's the centripetal force. And that force is Fc is equal to mv squared over r. At the bottom, the net force needs to be upwards towards the center of the circle, so the support force must be bigger than the weight force, which is downwards. So Fc is equal to F support minus F weight. Or we can rearrange that for F support to see that F support must be equal to the centripetal force needed plus the weight force. At the top, the net force needs to be downwards towards the center of the circle, so the support force and the weight force both contribute to the centripetal force. So we get this situation, which we can rearrange for F support to see that that's equal to the centripetal force minus the weight force. So the support force is much smaller at the top than it is at the bottom, because at the bottom the support force needs to cancel out the weight and then provide the extra. So the support force at the top is smaller than the support force at the bottom. If we look at the circular motion again, this time I'm dropping the ball from much further down, and so it's not going to be traveling at quite the same speed. So when we observe that motion, we see that at the top it kind of falls off of the loop because it doesn't have enough speed to get around. So we can analyze this in terms of what we know about the forces too. So if we go at a really slow speed, we'll just watch that again, oops. At a really slow speed, it reaches the top, but then it actually accelerates too quickly. It changes direction too quickly to stay on the loop. So the reason that's happening is that the weight force is bigger than the centripetal force that it needs to get around the circle, which means that at the top, the marble accelerates faster, so it changes direction faster than it needs to go around the loop, which means that it falls off of the track. We can figure out the speed at which this happens by noting that the minimum speed that is required to make it around the loop occurs when the centripetal force is equal to the weight force. So at that speed, Fc is equal to Fg. And that means that mv squared over r is equal to mg. If it's going at this speed v for this loop of radius r, then the weight force will provide exactly the centripetal force needed when it's at the top. So there won't be any support force at the top. If it goes any slower than this, the full weight force will still be acting on it, but that force will be bigger than the force required to take it around the loop, which means that it will change direction faster than it needs to and fall off. Okay, we can rearrange this for speed to get an equation for the minimum speed. So we see v squared over r is equal to g. So v min will be equal to rg square root. So this is a key equation. This equation tells us the minimum speed required to make it around the loop. So for a particular radius loop, there is some minimum speed required in order for the marble to make it around without falling off. If we go at any speed slower than that, the object will fall. If we go at a speed that's higher than the minimum speed, then we need some extra support force to provide the centripetal force needed. Because at a higher speed, it'll need a bigger centripetal force than the weight force. So let's have a look at an example. Jason swings a ball on a string in a vertical circle of radius 0.6 meters. We can label that in here. This radius is 0.6 meters. In fact, I won't label that in here because I'm going to draw a diagram here. It says, first draw the individual force arrows acting on the ball at the top and the bottom. So at the top and the bottom we have a weight force acting, and that's going to be exactly the same. So we'll call that Fg, and it's going to be exactly the same size up there. And we'll assume that the ball is moving at a constant speed, so we'll say that okay, and there will also be a tension force acting. So we can label that into, there's a tension force that's acting upwards at the bottom, Ft, and it'll be acting downwards at the top. And it's much smaller at the top than it is at the bottom. So to compare the tension forces at the top and the bottom, what we'll do is we'll just draw a little force diagram of each situation. So at the bottom, this is number 2. At the bottom, we have a weight force and we have a tension force that's much bigger than the weight force, and those two add to produce the centripetal force, or the net force. That looks like this. At the bottom, because the weight is trying to pull the ball out of the circle, the tension force needs to be really, really big in order to first cancel out the weight force and then provide the extra force needed upwards to produce the force required to move in a circle. At the top, the situation is a little bit different because now the center of the circle is below the ball. So at the top, we have a weight force acting downwards like this, Fg, which is still the same size as it was before, but in the same direction. And we have a tension force that's acting downwards like this, and it's very small. And those two add together to produce the same centripetal force that we had before, assuming that it's moving in a circle at a constant speed. So I haven't drawn the scale quite correctly. The orange arrow should be the same size here as it was on the other side. So in order to produce the same centripetal force at the top, a much smaller tension force is needed, because at the top the weight force is actually contributing to the centripetal force pulling the ball towards the center of the circle. Okay, the third one requires a little bit of a calculation. So for question part 3, calculate the smallest linear speed at the top before the string goes slack. The string will go slack if there's no tension in it. So the smallest speed at which that happens, before that happens, sorry, can be figured out if we just use that fact that Fc at the top is equal to Fg for Vmin. So any speed slower than the speed for which that's true, and the string will go slack. So let's put in the equations for those two things. We have mv squared over r is equal to mg. And we can cancel these m's, and therefore we can see that V should be equal to the square root of Rg, that's V min, which in this case is going to be the square root of, we were told that the radius was 0.6 meters, so that's 0.6 times 9.81, and then we can do that. 0.6 times 9.81, and then we'll square root it, and we get 2.43, 2.4 meters per second. Any speed slower than that, and the string will go slack. Any speed higher than that, and there will still need to be a little bit of this tension force at the top to provide the extra extra force required for the centripetal force. Okay. Let's have a look at another couple of examples. So here we have a roller coaster going around a loop without falling off. It's moving faster than the minimum speed at the highest point. Draw labeled arrows showing the size of the individual forces on the coaster at the top and the bottom. Draw labeled vector diagrams showing the size of the total force and explain your answer. Okay, so let's do that. So both at the top and the bottom we have a weight force, and because the roller coaster hasn't changed, the weight force will be the same in both positions. Note that at the bottom the weight force is pointing away from the middle of the circle, whereas at the top the weight force is pointing towards the middle of the circle. Okay, then we also have a support force in both situations. At the bottom the support force needs to be big enough to overcome the weight force and provide the extra force needed for the circular motion. I'm going to draw it a little bit bigger than that. That's F support now. And at the top, the support force is tiny, as we'll see from answering B. So this is part A. And for part B, right here at the top, we have the weight force, that's Fg, and we have the tension force, Ft, and those two forces add to produce a centripetal force, F total. Okay, and at the bottom, note that we're going to assume here that it's traveling at the same speed at the top and the bottom. In most cases that wouldn't really be the case, because the roller coaster's got to get up the hill to get to the top, so it'll lose some kinetic energy. But we'll assume that it's traveling at the same speed at the top and bottom, just so that we can compare these easily. So at the bottom, we once again have the weight force. I'll draw it like, oops, just to make it easier to compare, I'm going to draw the weight force down here. And then we also have a tension force. Oops, tension, green. The tension force looks like this. F tension. And we add those two, so adding them tip to tail as vectors, we get a total force that looks like this. And if it's traveling at the same speed, then the centripetal force at the bottom needs to be the same as it is at the top. So the two yellow vectors here, which is the sum of the other two, they need to be the same at the bottom and the top if the roller coaster is traveling at the same speed at the bottom and the top. So let's just write a brief explanation of that. I just want to change from this ugly color. Okay, so at the top, the weight force contributes to the centripetal force. So only a small, not tension, I label this as tension, that should be support forces. So this should be support and support. Only a small support force is needed. At the bottom, Fg is pointing away from center, so tension needs to be much bigger. Okay, so basically this shows that this situation is asymmetrical, and that's because the weight force is always pointing downwards, but the centripetal force always needs to be towards the center of the circle. Okay, finally we have a typical roller coaster problem here, where we have a roller coaster that rolls down the hill and goes around the loop. We're given the diameter of the loop here 15 meters. Maybe we should just remind ourselves so we don't make that mistake, that the radius is 7.5 meters here. And we have the roller coaster rolling down and going around this loop. So the first thing it asks us to do is calculate what is the minimum acceleration the coaster must have so it doesn't fall off at the top of the loop. Well, if it's accelerating, if its centripetal acceleration is exactly equal to the acceleration due to gravity, that's when it won't fall off. So basically, AC equals G, or 9.81 meters per second squared. The minimum speed the coaster must have so it doesn't fall off the loop, well, V min is equal to the square root of RG, which is equal to the square root of 7.5 times 9.81, which gives us 8.5776 meters per second. It should really be to two significant figures, so I'll say which is equal to 8.6 meters per second to 2 SF. Okay, so moving on, calculate the minimum height of the hill assuming the speed is 0 at the top of the hill. So this is a kind of tricky problem. We're going to need to use energy considerations here. So here we have mgh. Here, all of that energy, that's equal to E total. Here, it's gonna all be kinetic energy. And up here, at the top of the loop, it's gonna have a combination of kinetic energy and gravitational potential energy. And we know how much kinetic energy it must have at the top, because we know how fast it must be going to not fall off. So the minimum height is the height where it has enough potential energy to get it back to the top of the loop with enough speed that it doesn't fall off. Okay, so the easiest way to solve this is just to work out how much higher it has to be than this point. Whoops, it's a bit too low down. Than this point, so that loss here, that's delta EP, that must be equal to EK at the top. Because when it gets to this height again, it will have regained much of its potential energy, but it needs to still have enough kinetic energy to get around the top. So let's work this out. So EP lost at top. So in other words, how much potential energy has it lost when it is at the top of the loop? That's going to be mg times delta h, which is equal to, we don't actually, well, let's just work it out in terms of m, because we don't have the mass of the roller coaster. So that's going to be mg times h. I'll call this total height here that we're trying to figure out big H minus 15, because this height difference here, that's delta H, that's going to be whatever the starting height was minus the diameter of the loop. Okay, and then we can say EK at the top must be equal to half mv min squared. Okay, and we need to this potential energy that's been lost needs to be equal to the kinetic energy that it has at the top. So mg times h minus 15 must be equal to 1/2 mv min squared. And now you can see that we can cancel these m's. We weren't given a mass, remember? So conveniently we can cancel those m's. Now we know g and we know v, so now we can find h because it's the only unknown. So let's do that at the top there. So rearranging this, we get h minus 15. I'll just go eek, like that. H minus 15 is equal to v min squared over 2g, which is equal to, what did we have as our v min? It was 8.6 over 2 times 9.81. So, whoops, so h is equal to 8.6 squared over 2 times 9.81 plus 15, which is equal to I'll take this unrounded number and square it, and then I will divide that by 2 times 9.81. Oops. And that's 3.75. We need to add to that the 15, which gives us 18.75 meters. Okay, this last question just asks us to do the same thing, but symbolically. So we're not given r this time. We were given 15 before, which was 2r. In this case, we're going to have to work with just symbols. So again, we're going to start with EP lost is equal to EK gained at the top. So the EP lost was equal to m times g times the height of the roller coaster minus 2r. 2r is that diameter, and that's how high it will be by the time it gets to the top of the loop again. And that must be equal to 1/2 times m times the minimum speed squared, but the minimum speed is square root rg. So that's going to be square root rg all squared. So we can first just cancel the m's because that's convenient, and then we find that g times h minus 2r is equal to 1/2, but rg square root all squared just takes away the square root and the square, so that's 1/2 times rg, and now we see that the g here cancels as well, so we get h is equal to 1/2 r plus 2r. So that's just equal to 2.5 r. So basically, if we have a loop of radius r, we need to make sure that the roller coaster starts at least 2.5 times the radius above the top of the loop. Well, above the ground. Obviously, you'd want to go a little bit higher than that because you're going to lose some energy due to friction as well. So this is a minimum value. Okay, so that's kind of the way that we will apply these concepts, and I hope all of that makes sense. You will need to practice some more, first on the assignment, and then if you still feel uncertain about the things, there are extra problems provided as well. So to summarize this section, there is a minimum speed at which an object can complete a vertical loop of a given radius safely. If the acceleration required at the top is less than the acceleration due to gravity, then gravity will cause the object to fall out of the loop. The minimum speed is determined by equating the centripetal acceleration with the acceleration due to gravity. So basically we then end up with this equation, which we used in all of our examples. The minimum safe speed is the square root of rg. Okay,